Today I'd like to look at using integration by parts repeatedly in order to continually lower the complexity of the integral until you finally get down to something that we know the antiderivative of. And this can get quite messy actually, and so first I want to show you how it can get kind of messy, and then I'll show you a way of sort of keeping track of all that in a much easier way. So let's look at this example. X cubed e to the 2x, similar to the one we did before, but it's higher degree, and we do have a constant coefficient there in front of x, a non-1. So let's take a look. Same logic, though, as before. When we're thinking about what should be our u and what should be our dv, x cubed would be nice because the du will be a degree less. And e to the 2x is nice as dv because when I integrate that, although I'll pick up a constant, I won't make this expression any more complicated. I won't introduce other functions, just a constant multiple. So du 3x squared dx and v 1/2 e to the 2x. And now we'll apply the formula. So this is equal to uv. And to keep track of where everything's coming from, I'm not going to simplify anything as I go. Typically you would, but our shortcut will take care of that. I'm going to look at a shortcut afterwards. So I'm going to keep all of this unsimplified for right now. So uv, because I want us to be able to see when we're done where everything came from. So minus the integral of v du all right. So we did our integration by parts. And really, effectively, we started with a cubic times an exponential, and now we have a quadratic times an exponential. There's some constants floating around, but we have lowered the complexity, right? We haven't really changed the complexity of the exponential, but the polynomial's gone down a degree because of differentiation. So now I want to do integration by parts on this integral, and really the same logic as far as assigning my u's and my dv's. I'd like the polynomial to be u, because du then is simply 6x dx, and my dv will be the 1/2 e to the 2x dx, which when I take the antiderivative there, divide by 2, 1/4 e to the 2x. And now apply our parts here again. This was just the term we already had out front, our old uv. And we've got to be careful with that minus. It's minus this entire thing that we're doing, integration by parts. 3x squared uv 1/4 e to the 2x minus the integral of v du 1/4 e to the 2x times 6x dx. All right. So again, notice things have gotten a little better. We started with a cubic, we knocked it down to a quadratic, and now we're down to a first-degree polynomial. The exponential is just kind of coming along for the ride. It's picking up a half every time we integrate. So let's go one more time here. So again, it makes sense for the polynomial to be u and the exponential to be the dv. So that's 1/8 e to the 2x, and du 6 dx. And we have to be careful with distributing our minuses. You end up with a lot of minus times minus times minus with the repeated applications here. So we have x cubed 1/2 e to the 2x minus 3x squared 1/4 e to the 2x. Then minus a minus uv, so plus 6x times 1/8 e to the 2x. And then minus a minus a minus, so minus the integral of v du. And again, I'll keep those separate. How did I write it before? 1/8 e to the 2x, 6 dx. Okay. Now, let's just take a step back and notice what happened. And this will be the idea for our shortcut. There's a lot to keep track here, right? And if this degree is, say, 6th degree, you'd have to go through this 6 times, right? Every time we go through, notice u is x cubed, then u is 3x squared, then u is 6x, and then now we're down to a constant. We can just integrate this last bit. And then the dv, e to the 2x, 1/2 e to the 2x, 1/4 e to the 2x. So look what happens here. This is our original function, derivative, then the derivative of that is 6x. Here, this is the integral of our original v, or excuse me, dv, integral, integral. So really all we're doing is starting with that x cubed and differentiating over and over, starting with e to the 2x and integrating over and over. So we'd like to just keep track of the derivatives and integrals and not all this notation in between. So we would finish up here. This last one is just so after doing all this work, we should at least finish the problem. And then one more integration here would give us 1/16 e to the 2x. And then times that constant, 6. Okay. So think about how we could have done this without all this writing. And there's plenty of places to make a computational error here, lose track of a minus sign especially, before you get down to the bottom. So instead, we can do just sort of a bookkeeping approach of what are all those u's as you go, and what are all those dv's as you go. So we start off with u being x cubed, and dv is that e to the 2x dx. I'm just going to write the e to the 2x for shorthand. Now I'm just going to differentiate to generate these terms. So we're going to see how we could get to this answer much quicker than all of this. So 3x squared, 6x, 6, nothing. Over here, I'm just going to integrate. And now how did these guys end up paired up in our answer? Well, the very first pair that you generate is u, not times dv, but times v. So it's your original u pairs up with that first antiderivative, right? Then the derivative of that pairs up with the next antiderivative, and so on. And I just write that 0 in there as a placeholder. It reminds me how many antiderivatives to take over here. That 0 doesn't really get paired up with anything, but it's just there as a placeholder. So that gives us all our pairs. Notice how quick and easy that was. But we also have to account for the minus sign, right? So what's happening here? The very first time through, you get a minus. So that makes that second term have a minus. But then the third term is a minus, so it's plus. And this term's a minus, which is a minus. So we get this alternating of plus, minus, because of that repeated application of the minus in that formula. So I just make a note to myself that I'm going to have to insert a minus on that one and a minus on that one, just skipping, if you like, plus, minus. And that's exactly what we have here, right? So you could do all of this work, or you could just generate this little table here. So definitely do this, because especially as that degree gets higher and higher, this just gets worse and worse as far as how many times you have to go through it. So you can use this thing here, which is called the table method. It's not a new technique, because we're doing integration by parts. We're just recognizing that there's a way to skip over all the details. Underneath this is really still integration by parts over and over and over again. So when can we use this table method? Well, let's think about this. What makes this process work? What is it about this that makes it have an ending? And it's really this. It's the fact that if you differentiate enough, you eventually get down to that constant 6, right? Because that allowed us to integrate the exponential. So this is going to work if your u is a polynomial. Because anytime your u is a polynomial, the integration by parts is just lowering the degree. And polynomials, if you differentiate them enough times, will eventually get down to a constant. So any situation, integration by parts, where you find yourself starting out with the u being a polynomial, this table method will work as a shortcut. So this is not something you can use in every integration by parts, but if the u is a polynomial, then this table method will work. Just be careful about assigning your signs there and getting your derivatives and antiderivatives correct, and you should be okay.